few more. There's Leslie. Johan, awesome. Awesome. One more. Okay, well, that's where we will have to begin. Good afternoon, everyone. Hello. Welcome back to a wonderful action-packed day of geometry. We've got some incredible stuff going on today. I don't know if you noticed, especially if you got to level 3 and watched that video on that problem set. Ooh, we're in for a doozy, okay? We're going to run through the answers for problem set number 1, and then in analyzing some of those answers, it's all going to culminate in this new question about the relationship between surface area, perimeter and area. And then related to that, when we go one dimension higher, we'll then compare area to volume. Okay? But right now, perimeter to area, what can we surmise about the relationship between the two for various shapes? So with that in the back of our heads, let's go ahead and take out your problem set number 1. Let's walk through the answers. Stop me for further explanation at any time. I'm going to try to move relatively quickly here. We started off with just straight up find the perimeters. Yeah, they're irregular, but that's okay. Just add up all the numbers, okay? Make sure you watch what is congruent to what. Make sure you include your units. Okay, this little symbol, this double apostrophe here means inches. So you can write it in either format, but you have to include one of them. Next up, we bring back our good friends, the tetrominoes. Yeah, Tetris never dies. What is the maximum and minimum perimeter possible on tetrominoes? Well, most of these, actually, there's only 5 unique shapes. Flipping and turning them doesn't change anything. But most of them have 10 units for their perimeter. Inches, centimeters, whatever scale you want to put on your tetrominoes, okay? 10 units. And only one of them, the square, has 8. So the maximum is 10 and the minimum is 8. There we go. Oh, hey, Wendy, you made it. Awesome. Okay. Take out your problem set. We're running through the checking our answers. So next, question 7. We're arranging toothpicks to form rows of shapes and counting perimeters there. And we find actually several patterns going on. So within the triangles, however many triangles we have, that's n triangles, we have n plus 2 toothpicks for our perimeter. For squares, though, we have 2n plus 2 for our perimeter. And for pentagons, we go to 3n plus 2 toothpicks in the perimeter. Hexagons is 4n plus 2. You see the pattern here? Like, not only was there finding the pattern horizontally, right? How many toothpicks in the perimeter, not just total, so we don't count these inner zigzag ones, just around the outside for making these rows, find the pattern there. And then vertically, there's another pattern emerging because we're always adding 2. And we go from n to 2n to 3n to 4n to now 6n. Oh, wait a minute, why did we jump? Well, because we jumped from 6 sides to 8 sides. So overall, for an m-sided polygon, or m-sided polygons, n of them in a row, we have m minus 2 times n, all plus 2. That's kind of neat. I like that one. Pattern within a pattern there. Okay, number 12. This one is critical to our exploration today. A square and a circle, both made out of wire, enclose the same area. Okay? That's important. It doesn't mean they're the same width or height or any other dimension. It means they have the same area. And then you undo the wire, okay? Flatten it out, straighten it out, and measure how long is the wire. Now that wire is effectively, since it went around to form the shape in the first place, it was the perimeter. So we took the perimeter of a circle of a set area versus the perimeter of a square. I can't make a solid square with my hands, right? I'm trying on right angles here, okay? How do those perimeters compare if the area is kept the same? And the answer is that the square will always be longer, and specifically for this given area, it will be longer by 1.95 centimeters. Here's something else to think about. How about scaling? What happens when we make things bigger? Well, remember, length and width are linear single lengths. Area is a quadratic length. So if I multiply both length and width by 2, so I take my rectangle, it has a given area. If I were to make it longer, it would have twice the area, right? If I were to make it twice as wide, it would have twice the area. Either one of those by themselves doubles my rectangle. If I do both, I double and then double again, I have 4 times the area. Multiply both by 3, 9 times the area. By 10, 100 times the area. By whatever n squared times the area. That's the quadratic nature of area. Okay. And then here we just have some standard calculate area practice for some right triangles. Nothing terribly tricky there, just turning that into a habit. On C there, because of the irrational, you'll have to round. We went with 2 decimal places here. You could do 1, 2, 3, 4. I don't really care. Something reasonable. Please don't truncate down all the way to 17. We don't want to imply that the answer is, in fact, an integer when it's not. Otherwise, they didn't tell you how many decimal places to round to, so that's what we get. Any questions from the level 1 problems? Okay, then let's go on to level 2. And if you didn't do the level 2 problems, please pay close attention here as I explain through each one, because this is where we will really see that connection between perimeter and area that I'll be asking about at the end. So first up, tetrominoes were great. Pentominoes are even better. They are 1 better. 5 squares. So if I lay them out in a line, we can easily count. You'll have 12 units for your perimeter. And there's many other of the pentominoes. There are a whole bunch of them. I didn't want to redraw all of them. But any of them that have in a line or a single bend, or even 2 bends, like so the zigzag and the L, all of those will have a perimeter of 12. This guy is the only one that has a perimeter of 10. You see what's different and unique about this one, as well as from the tetrominoes. What stood out about that one that had the minimum perimeter? Can we follow that same pattern? We had maximum of 10, now a maximum of 12. What if we go all the way out to an octomino, 8 squares connected together? Well, in a straight line is at least the simplest to draw. It's not the only option, but you will get a maximum perimeter of 18 and a minimum of 12 if you arrange them like this. Now this is a great reference because all of these have the same area. This is 5 squares, this is still 5 squares. This is 8 squares, this is still 8 squares. So we're looking at the different arrangement of the area can change the perimeter, or more or less. Come back to that. How about this setup? Number 8 had us arrange a square of toothpicks. In this case, we went with 7 by 7. So all the way around, the perimeter is 28 toothpick units. The area is then 49 units squared. Straightforward, simple square. Part B is where we start changing things. B, here we have rearranged the corners and we've kind of like poked it in. Like imagine you pushed into the balloon here. Right? So these toothpicks are still there, they're just now indented into the square. Which means that 1 by 1 square of area is no longer part of the enclosure. It's not included. We have to subtract out all 4 corners. So instead of 49, we have 45 square units of area. But the perimeter is still the same. And C goes 1 level higher. What about a 2 by 2 square taken out of each corner? Okay, subtract that off. Your area is left as 33 units square. Perimeter, still the same. So with the pentominoes, we kept the same area and made different perimeters. Here, we keep the same perimeter and we're able to make different areas. Compare, contrast. 3 squares in a corner gets you same perimeter down to 13 square units of area. Overall, what is happening? The perimeter stays constant. For whatever size of large square you can create, the perimeter will always be 4 times that, 4m, or m toothpicks per side. The area, however, decreases as the corner squares increase. So your area is always going to be m squared, the big square size, minus 4 times n squared, n being the size of your little square. Okay. Here's another example. Problem 21. Suppose 2 rectangles have the same perimeter of 40 meters. Do they also have to have the same area? This plays right off of this one. Keep the perimeter the same. Do you get the same area? The answer should clearly be no. We just saw it up there. Of course, those weren't rectangles, so let's be sure. Here's an example of rectangles. Okay? 15 by 5. Add those up, double it for the other sides. Perimeter is 40. Multiply the 2 to get area of 75. But I could also make a 10 by 10 square. Square is a type of rectangle. All add up to perimeter of still 40, but the area is now 10 times 10, 100 square units. So with the same perimeter, I am in fact able to get a larger area, still maintaining rectangular shape. So what is different about these rectangles? Same thing that is different about these rectangles. We're getting somewhere. We're getting somewhere. Keep that in the back of your mind. 26, more practice on just running the formulas for triangles. This time with non-right triangles. So you have to make use of that given altitude. So there's the answers there. And then here is triangle C. Any questions from level 2 problems? No? All right, then let's take a quick look at level 3 where we get our first real brain bender. So 27 is an interesting one to look at. This is directly comparing rectangles and triangles, pitting those 2 formulae against each other. They tell us that side ED, that's all the way across here, is twice the length of CD. So I've gone ahead and marked that says this segment CD is congruent to EC. Right, that makes sense. If I've doubled the length, then I have to add in the same amount off the end there. And And so how do the areas of rectangle ABCD compare to triangle AED? The answer is they are perfectly equal. Think about how you would calculate each one. To get the area of the rectangle, I'm going to multiply the length of the base times the height. Okay, so that would be AD times CD, whatever those numbers are. You have to work abstractly here for a moment. Work without the numbers, just conceptually. I'm going to multiply this thing by that one. For the triangle, I also want base. In this case, it's still AD. Hey, that's the same thing as before. Whatever the number was, it's going to be the same one here. Times DE for the height of my triangle. And I know they told us the height of the triangle is going to be twice the height of the rectangle. So on its face, it sounds like, wait, you said it's twice as tall, therefore it's twice as much area. But it's a triangle instead of a rectangle. The relationship there is that triangles are half the area. So I take my rectangular area, I double it for double height, and then I halve it to make the triangle. So those two process, double and half, undo each other, and I'm back to the exact same amount I started with. That's kind of a neat way to think about things. All right, the last one, and I included the video accompaniment to go along with this because this is a classic, fascinating problem. You have two coins, one with a radii of 3, another with a radii of 1. So effectively, this coin is 3 times the width of this coin. I have no idea what actual real-life coins these would be with such extreme differences. And then what I'm going to do is I'm going to roll this small one around the outside. Okay, maybe not quite as many spirals, but it's going to roll across here. And I mean actually roll, not just slide, no slips, okay? Pretend they have like gear teeth and they mesh into each other. And so it's going to roll and chug along there, right? It's going to gear and mesh all the way around the other one. The question is, after it completes one trip all the way around and ends up back here, how many times has it itself spun in place? Okay, if I was to make a mark on here to indicate a direction, how many times does that spin around? Like it spins and rolls and up and ends up up over here, and it's still upright again. And it goes around again and is upright. That's what we want to try to figure out. When you first think of this, your gut tells you it might be 3. And you have a very good reason for thinking it's 3 times. Because the radii is 3 times as big. Oh, you can't trick me, Mr. Apple. The radius isn't the important bit here. I know that it's the outside of the circle rubbing against the outside of that circle. I need to compare their circumferences. You are absolutely right. But the circumference is just pi times diameter. Nothing gets squared. So if one is 3 times as wide, the circumference is also 3 times the distance. It is absolutely true that this large coin is 3 times as far around as the small coin. In fact, if I was to make these circles out of wire, just like that previous question, and straighten out the wire on each one, this one will be 3 times the length of that one. So it absolutely makes sense to say, well, if I roll one length of this circle, if this goes all the way around, rolls along the ground, one circumference of itself, it's going to go a third of a way, and then another third, and then another third, right? It'll take 3 times to get around. Yes, you are correct. It will take 3 of its own circumferences worth to work its way around this circumference. But the actual answer is 4. It rolls 3 times its own circumference in distance, but it rotates a total of 4 times. Why? Why the heck is it 4? Where does the other circle come from? Where does it get that extra rotation? This is the paradox. It's not really a paradox. It's not truly contradictory, but it is counterintuitive. In fact, this is so famous, it has its own Wikipedia page. It's called the coin rotation paradox. So let me read you that definition there. The coin rotation paradox is the counterintuitive observation that when one coin is rolled around the rim of another coin of equal size, the moving coin completes 2 full rotations after going all the way around the stationary coin. That's so weird. But here it is. Take a look at George Washington in action. Okay, we've got the tails side quarter stationary there in the middle. We've got the head side up quarter rolling its way around. So again, quarters are great for this because they actually have the little ridges. They can almost mesh like gears. You would think, just like gears, hey, if I took 2 equal sized gears and meshed them into each other and spun them around, as one spins all the way around, the other will make one complete revolution. It should be 1 to 1. For 2 free spinning gears, you would be correct. But here's the rub. In this scenario, they're not both spinning. One of them is stationary. That's the difference. The guy in the middle doesn't move, doesn't rotate. So in order for the moving quarter to get all the way around, it has to pull double duty, as it were. It has to impart on itself the motion that would have been there if the other gear was also turning. So this has to turn its own rotation and complete the rotation to go around the other gear or the other coin. Look at this. George Washington is doing a full 360-degree flip, but he's only rolling over the top half of the coin there. We can clearly see that if he was to continue and go around the bottom half of the coin, he would have another revolution. If I spun both coins at the same time, this wouldn't happen. I would get the 1-to-1 matchup. There's 2 circles that are turning. So if only one of them is doing the moving, that one coin has to move 2 circles worth. Is it starting to make sense? How about our example? What about unequal radii? And we won't get to the other shapes, but the unequal radii, right? This is specifically our scenario. We have one coin that is 3 times as big as the other. So if you take a circle, and we'll use this wonderfully rainbow-colored ring as our coin stand-in, so we can see what way it's facing with that arrow there. And it's going to roll along. And you can see we've created a little road for it, a little track to roll along. And the track colors match up precisely to the coin's edge colors. So we start with the gray on gray. And as it rolls a little bit forward, we get the dark gray on the dark gray. And then you can see here in the second circle, the arrow is now pointed fully to the right. And the purple section of the circle lands on the purple section of track. And then it continues to roll until the arrow points down, then it points left, and then it points up again. So I've got one full rotation there on screen. So we've taken the circumference of the circle and flattened it out and said, hey, if you roll that length, you will make 1 revolution. That's well known. That's firmly established. That makes sense. We do that 2, 3 times. We roll 3 times our circumference. We rotate 3 times. All well and good. Until we want to go back to the coin around a coin. Why is that different? Because we're not rolling on a flat track. What if you took your track, picked it up, and bent the track now into a new circle? That's where we get the 4th rotation from. The track itself imparts an extra rotation. Take a look at this diagram now. Again, we start up here, arrow pointing up. We've got black and gray on black and gray. We roll a little bit more. We're now pointing, well, it's not quite to the right exactly. It's kind of down to the right, but we still landed purple on purple, right? And we still land green, yellow on green, yellow. Look what happens here. When we land on red, now our arrow is pointing straight up. We've completed one full rotation. But relative to the track, it's not till we get to this, say like 4 o'clock position, that we're back to black and gray on black and gray. This arrow here in the 4 o'clock position, there, centered on screen, is not pointing up as we would call it, right? From outside the circle looking at this, we would not call that up. But imagine, if you will, this is the surface of the Earth, right? Down there in South America, they would still point away from the Earth and call it up, just like we do up here in North America, right? This arrow is not pointing up, but it is pointing away from the circle, away from the track surface, just like it started, pointing away from the track surface. So relative to the track, we do have 3 rotations, one there at 12, one at 4 o'clock, and one at 8 o'clock. I'm using clock face to denote positions because I don't have my laser pointer. There are 3 such positions around the circle that the arrow is pointing away from the circle. So that's 3 rotations relative to the circle. But relative to us, relative to the rest of, space, the track itself is another circle. So we end up with 4 objective rotations, right? Instead of relativistic, it's absolute, right? 4 absolute rotations of the coin. So the true answer to the coin paradox is 4 rotations when one coin is 3 times as big as the other. Isn't that wild? Okay. If you still haven't wrapped your brain around that one, don't worry. I want you to go back to the the perimeter to area ratio. We haven't gotten to surface area yet. We'll get there. This is my question for you. Take a look back at, say, the toothpick outline or the tetrominoes and pentominoes, and I want you to tell me what kinds of shapes have the highest perimeter to area ratio, and what kinds of shapes have the lowest perimeter to area ratio. And I'm actually going to go ahead and post this on Google Classroom so you can type your answer there. Okay, there it is. Same question. How would you describe those shapes? Again, we can look at, if you just want to think in terms of rectangles, for a second, go to the pentominoes or the octominoes, right? How would you describe this rectangle versus this bunch? Or specifically this rectangle versus that rectangle? Which adjectives of the English language would you actually use to describe one in comparison to the other? Hey, can you hand me one of those rectangles over there? Yeah, which one? The blankety blank one, right? Well, what would you call it? How would you describe it? Because one of them, well, actually, let's start here. They both have the same area, but one has more perimeter, one has less. So this guy has a higher perimeter to area ratio. Imagine actually dividing those numbers. Calculate the perimeter, calculate the area, and divide. Perimeter divided by area. Who gets the bigger number? This guy here. Who gets the smaller number? This guy down here. And if you're feeling so bold, you can try to generalize that. This question, these guys from question 8 can help with that. What is happening to this square as we take out the corners? Can you generalize to any type of polygon, not just rectangles? Which types of polygons tend to have highest or lowest? Or as you add sides to the polygon, what happens? Does the ratio go up or down? What happens about circles? Where do circles fit in that? Circles are kind of an extreme case because they have no sides. They're infinite number of points around a center. So do they have the highest perimeter to area ratio, or do they have the lowest perimeter to area ratio? This is all the same question. So one final way, if you are still unsure, pretend you're playing Minecraft for a moment. Don't actually boot up the game, please. And you want to build a sheep pen. My terrible handwriting here, I apologize. I wrote this really hastily. If you want to enclose a space for your Minecraft sheep, you only have so many fences. Okay? How do you get the most area for your fence? You want the lowest possible perimeter to area ratio. So you get the biggest bang for your buck, as it were, the most space to keep the sheep in for the fewest number of fence posts. What kind of shape would you prefer to build? That's the question we're considering here. Okay, so go ahead and take a few minutes, ponder that in your brain, and type up an answer for me on Google Classroom. And then in a few minutes after I've got a few answers in, I'll go ahead and we'll discuss what we've got so far, and then I'll introduce problem set 2 to you real quick. A few things I would like to highlight. let's take a look at some of these. We'll stick with rectangles to be simple here. If I was to draw a couple of sample rectangles here, there's one. And actually, we're gonna go even more extreme. There's two. We'll call this rectangle 1. We'll call this rectangle 2. Tell me in chat which rectangle has the highest perimeter to area ratio, rectangle 1 or rectangle 2? There we go, I've got one response. Anyone want to back that up? Take a vote, 1 or 2. Yeah, that's right, rectangle number 1. This has the highest perimeter to area ratio. Imagine I had to fence this in. You know, I've got to run my fence all the way down here, all the way back, and I get not a lot of area in it, right? If you were to fence in a backyard like this, you would not find that a great place to play. Whereas here, right, I've got a lot more open space. It just feels bigger, right? This has a much lower perimeter to area ratio. So I ask you, how would you describe these rectangles? What adjective, how would you describe, if I said, tell me the difference between these two rectangles, what adjective would you use to describe this guy? Rectangle number 1. What would you call it? First thing that comes to mind. It's the Vanessa says wide. Anybody else? Keep in mind, I could also rotate it. What if it was spun up that way? Tall. Yeah. Skinny. That's the first word I came up with. Skinny. Right? Long. Tall. Something like that. What about this rectangle? How would you describe number 2? Certainly relative to number 1. Okay, how would you describe this guy? Short. Right, he's not tall. Short is also opposite of long. You can almost call it fat. Right, opposite of skinny. Okay? Something like that. You can clearly give a descriptive difference between those two types of rectangles. Now, if we wanted to be more precise here, right, we've got to come up with a generalization that applies to polygons as well, because our polygons will also, I wanted a square. Close enough. 1, 2, 3, 4, 5. Yes. 1, 2, 3, 4, 5, 6. Yes. Our polygons also make a progression. As I add more and more sides, okay, dot, 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 the most sides possible. If I go all the way out to infinite sides, we've effectively created a circle, right? And what did we learn about a circle compared to a square in the area to perimeter relationship? That came out of, what was it, question 12 with the wire? Right here, right? For the same area, the square perimeter was longer, which means which one had the greater perimeter to area ratio, square or circle? The square had the larger perimeter. Area was kept the same. So perimeter to area ratio is higher on this end and lower on this end. Right? Squares, and we can go one further, right? 6, 5, 4, down to 3. The triangle is the absolute highest perimeter to area ratio possible, as far as a regular polygon. And I wish I could have gotten this guy to be a better equilateral triangle, but close enough. And the lowest possible perimeter to area ratio is the circle. It's the most round. So the more sides I have, the closer to round I get, the better, or the lower my perimeter to area ratio is. So if that's what you're aiming for, if the best possible means the lowest, you want to go with the circle. If the best possible means highest ratio, you want to go with a triangle. Okay. Oftentimes we're trying to go for the lowest. We're usually trying to maximize area for a given perimeter. That's what you would do if you were building a sheep pen, right? In Minecraft. You want the most space for your sheep, but you only have so many fences to go around. You want to get as close to a circle as you possibly can. That's why a perfect square is better than a long, skinny rectangle. And then even closer to a circle gets you better and better. It's hard to approximate circles in Minecraft, I know, but you can at least do this. Isn't that neat? And then we will continue this idea. So keep this in the back of your head when we get to volume and we start compare surface area to volume. Okay? Because then we go into the realm of 3D. That's how real life, but this same idea also extrapolates to there. And you may have heard about the surface area to volume ratio in biology or chemistry class. This occurs in nature and science. This is a big deal, and it's what makes things happen. It's also why you get the most pizza for the smallest amount of crust with circular pizzas, right? Things like that. Okay. Any final questions or thoughts, concerns on these ideas? No? Okay, then let me give you a brief introduction to problem set 2, and then I'll give you 5 minutes there to get started. Problem set 2 introduces a whole bunch of cool new things and the problems, first and foremost of which is Heron's formula. This is a super useful tool for finding the area of a triangle when it's not a right triangle. You can actually find the area of a triangle just from its 3 side lengths. Yeah, you thought it had to be a right triangle or find that altitude thing every time. Nope, Heron, another ancient Greek guy, found a way around that. Very handy, super useful. 40 introduces Sierpinski's carpet. You may remember Sierpinski's triangle. It's that triforce within a triforce within a triforce thing. Sierpinski's carpet is the same idea, but squares. Super cool, fun to play with. Go ahead and explore that in question 40. 42 has got atom smashers. 43, we've got the good old carpeting your floor plan. Great practical application practice there. Lovely problem. 38 introduces this new thing called Pick's theorem. Again, named after a guy named Pick. This is one that was new to me, but it's a way to estimate area for when more precise calculations are more difficult. So you can use that to find the area of Oklahoma. Okay, kind of fun. And 30 walks you through an interesting, it actually does kind of help you build your own proof about the areas of triangles. 51 is more tires on the road. 52, this last one is really neat. It is about the staggered starts on a racetrack. So if you ever watched a foot race around the oval track and wondered why they don't all start at the same spot, they're back for, it's because the guy going around the outside has to run farther, and you can actually calculate what the appropriate staggered start to make a fair race would be in that problem. All right, so with that, no, I'm off by 5 minutes. I'm sorry, I didn't get you 5 minutes to work. That's it, we're done, okay? You have those are due on Friday. Have fun. So long, farewell, enjoy the rest of your day.